we just did pre-lab exercise 1, which was basically a hypothesis test on numeric datas. So here, like, what is your GPA? This is a measurement that's recorded as a number. And now here in pre-lab exercise 2, what we're going to do is investigate a hypothesis test that's on a categorical data point. So mainly here, I'm going to be talking about this marijuana use. So 0 represents no and 1 represents yes. So this is not a number to be measured. This is just, are you in this category? Yes. Or are you in this category? No. So the no's are represented with zeros and the yeses are represented with ones. So in the last video, I did show you a few things. For example, if I sum the data that is in the marijuana use, how many ones do I have? It's nice to add these because zeros, when you add a 0, it doesn't do anything. And then when you have a 1, then that really just adds up where the ones are. So if I was to look through this, then I would have been able to count that there were 25 ones somewhat distributed throughout these columns, and the number of columns itself was 101. So here, the sample proportion, okay, is that there are 25 yeses out of 101 tries. So somewhere around, not surprisingly, somewhere around 25%. So about 24.7-ish percent of people saying yes. Okay, so when we're trying to investigate that here, when we're reading, if somebody wanted to ask the question, does the data indicate that the proportion of students who have tried marijuana in the past year is more than what it has been? And here, what it has been, I guess, is 23%. So is the value 0.2475, is that bigger than the value 0.23? If you're just looking at the numbers, the answer is obvious. Yeah, the number 0.2475, blah, 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 is obviously a bigger number than the value 0.23. So on the surface, that's obvious. The question that we're trying to answer is 0.247 significantly bigger than 0.23? Or is this just like you don't always get exactly what you expect when you're doing random sampling, right? I mean, even if the value was supposed to be 23%, isn't it likely that, depending on who you ask, things could change? So that's really what we're saying here is, here, this number is obviously not 0.23, but is it far enough away from 0.23 to be considered something much different? Okay, so that's what we need to go through here. So here, how I'm going to write the hypothesis, and the important parts of what happened here is originally what we believe. So this is the hypothesized value. Excuse me. We are comparing our value, our sample value of 0.247 to what we thought it should be, which was 0.23. The other really important word that we've discovered here is the word more. So here, more just means greater than. Greater than does not include the equal sign. So here it goes into the null, meaning that here the complementary sign of greater than is going to be less than or equal to. Less than or equal to does include the equal sign, so less than or equal to does go into the null hypothesis, whereas the value or the value more means greater than. So this would be the correct way to write the hypothesis. And unlike pre-lab question 1, where we had a less than sign in the alternative, making it a lower tailed test, here we've got an example of an upper tailed test, a greater than sign. So here, things are a little bit mirrored from example 1, and the critical value and the rejection region will lie on the right. So one thing that you're learning then is the rejection region is really set up by the symbol that is in the alternative hypothesis. Some other things that we've learned already. This is what our sample said. Our sample said that there were 25 yeses out of 101 tries. Okay, so how do we find the test statistic? and go from there. Let me just quickly start setting some things up. Here, this time for proportions, we do use the Z distribution. So when you're talking about numeric data or number data like GPA, we had the option of using either Z or T. We decided to use T because we didn't know what the population standard deviation was. We only knew the sample standard deviation. When you're dealing with categories, in this course at least, we're going to use the Z distribution. Okay, so we don't exactly know what the test statistic is yet from this question. I'll calculate it later. But here's what we do know. It is actually a right-tailed test. So if I'm going to use the Z distribution, and then put 5% of the area, which is the rejection region, on the right because of an upper tail test, then here's where 5% is, and then here's where 95% is, and the value that's associated with this difference, the point in between these two values is the value 1.6449. If you want some more decimals here, let me just whatever. So here you've got, this is what the rejection region is. Okay, so here this is 5% in the right tail, and here the critical value associated is the value 1.6. If you want a little bit more on this, I talked quite a bit about this in the first exercise video, so you can go back and review that. What we need to do now is find what the test statistic is. So again, if the test statistic happens to fall on the right side, in this case, because it's an upper tail test, so here, if the test statistic falls on the right side of the critical value, that's when we'll reject the null hypothesis. And if the test statistic falls on the left side of the critical value, that's where we would fail to reject the null hypothesis. Here's the formula for finding yourself the test statistic. So here, this is the sample proportion, which was 25 out of 101. And then here, P represents the hypothesized value. So here, P hat is the value that's coming from your data that you've collected or your sample. And then here, P is coming from your assumption in the null and alternative hypothesis. So here, the P's are the 0.21s. So after calculating the test statistic, okay, so again, what did I do? I just, oops, sorry. I wrote this into R like it was a calculator. You can do it on paper if you like. But what I did was I calculated this value, which ended up being 0.4185 and change. Okay, so this is called the test statistic. Okay, so here, let me just put the test statistic onto our picture. Okay, so here, again, remembering if my test statistic was greater than this value, I'll reject. If it's less than this value, and by this value, I mean here, the critical value, then I will fail to reject. So if I put this value onto my picture, you can see in this case, this time my test statistic is actually closer to the null hypothesis than this critical value. So here I'm actually closer to what I thought I would have than some sort of outside tolerance value, meaning that I'm not inside the rejection region like I was in the first video. So here, this is an example of when you would fail to reject a null hypothesis. Again, you can either compare here test statistic to critical value, or you can compare alpha, which is 5%, to p-value, which is about 34% here. So here, this red shaded area, this red shaded area, that's 5% of the curve, and this green shaded region is about 34%, or the p-value. One thing that is different from the first video is in the first video we had all left tail things. And that was because the sign in the alternative was less than in the first example, but now the sign in the alternative hypothesis is actually greater than. So now you've got all of your tail probabilities coming from the right instead of coming from the left. Okay, so here alpha is coming from the right. This is here 5% from the right to this point, and the p-value is also coming from the right, whereas in the first example, it was both of these probabilities were coming from the left. So like here, if I put two tail, or if I put left tail, so here you can see the outside tail is the left side, but now the right side tail is the outside. Okay, so it's very obvious. Hopefully, it's clear to you that it's very important to get the sign in the alternative correct. Okay, so how do you actually find these values? I've used this sort of visual and it just popped these values up. But how did I actually calculate these values? So how do I get here the value that's associated with the test statistic? The value that's associated with the test statistic is called p-value. Okay, so if I was just looking at this chart here, here's the test statistic, which we just calculated to be 0.42-ish. How do we find here the right tail area? So, going back to Stat 213, in this case, when you use P, that's looking for probabilities. When you use Q, that's looking for values. So yes, I am looking for a probability. The distribution in this case that I'm using is the normal distribution, because I'm using the Z distribution, not the T distribution. And so here I can put in uh, the test statistic. But you have to be careful because here, remember, and this is why drawing pictures is so important. What we're looking for, which value is the p-value? Is it this area or is it this area? In this case, remember the p-value is always on the side that the alternative hypothesis is indicating, right? So here, the alternative hypothesis is saying that it's the side, it's the right side, it's this side, not this side. It's the right side, not the left side in this case. If your sign in your alternative hypothesis happens to be less than, then of course you would have the other side. So we have to be really careful about things, little details like this. So here, in this case, because we want the right side, not the left side, we have to do 1 minus this p norm because we want the right side of the area. Um, Alternatively, how did I find what the critical value was? How did I find here what the critical value is? Here again, the area is on the right side, right? So how much area am I going to put in here? Well, this is the probability of making what's called a type 1 error. We'll talk about that in class if we haven't already, or the level of significance. So here we want 5% in the right tail. Again, why right tail? For the same reason that the p-value is on the right. This is the alternative hypothesis. Sign is greater than. So here's the right tail test. So here, if there's 5% on the right, that means that there's 95% on the left. When I have the area and I want the value, instead of doing P norm, I need to do Q norm. And here the area on the left is got to be 95%, and the area on the right is 5%. So here, if I do what is the value such that 95% of the area is on the left, then that's Q norm of 0.95. And here you can see this is what the critical value actually is right there. Okay, so in this case, when you draw the picture, either when you're comparing test statistic, that's this yellow mark, to critical value, that's this blue mark, you can see that I'm failing to reject. Or if you're using p-value approach, if you've got a p-value of 0.34, so about 34% for the p-value, that's obviously bigger than the p-value, than the alpha or the level of significance of 5%. So 34 is bigger than 5. So in this case, either way, the indication is that because p-value is bigger than alpha, that means you fail to reject. Or in other words, because your test statistic is closer to the null hypothesis than some sort of rejection region, that means that you are observing something close to what you expected to. Here's how we write the p-value probability expression. Again, I explained this in some detail in the first video, but here the probability this time, the distribution is actually the Z distribution, not the T distribution. So here the p-value is the area such that if I'm using the Z distribution and I've calculated the test statistic, then because the alternative sign is the greater than sign, then the p-value is the area on the right of the test statistic. So here I've written that by saying the probability of when you're using the Z distribution being greater than, because this is the same sign as this, then the test statistic, which we just calculated here, happens to be this value. So that is what the p-value is. So again, in this case, when the p-value is smaller than alpha, that's when you reject the null hypothesis. And when p-value is greater than or equal to alpha, that is when you fail to reject the null hypothesis. Let's just remind ourselves what the null hypothesis was. So here I've written it here. I've rewritten it here. Our null hypothesis was that the proportion of students was less than or equal to 23%. And the alternative was that it was greater than 23%. And in this case, the p-value was bigger than alpha, so we fail to reject the null hypothesis, which means that this is the hypothesis that appears to be correct. So here what we're saying is it appears that p is not significant. So this doesn't look right. So it appears that p is not significantly greater than 23%. Maybe it's less than or equal to 23%. So that's what we've come up with here. Finally, what is the actual context of the p-value? Again, this is a statement you're going to get used to. It was the same statement that was in our first example. Here it is in the first example, and here it is in the second example. Again, notice there's pretty much no difference. Assuming the null hypothesis is true, the probability of observing stronger evidence against the null hypothesis is the p-value. Okay, and so that brings us to running a hypothesis test um, with a categorical information as opposed to numeric information, which was the first example.